This is problem 3-137.E. It's on page 174. A base for moving heavy machinery is designed as shown in figure P3-137. How much load could the base support based on the bearing capacity of the steel plate if it is 1 1/4 inch thick and made from ASTM A36 structural steel? Alright, look on page 174 if you are not already, and you'll see the base and the wheels and all there together. Now, there's some assumptions that have to be made here. First of all, the load that's applied to the base, I would assume that that load should be applied to the center of the base, not just directly above either wheel. If it's above one of the wheels, then what I've done here is wrong, because I've assumed that the load is evenly distributed among the two wheels. There's some other things to talk about here, but let's start off with what we know. If we look up ASTM A36 steel in the appendix, you'll find that it has a yield strength of 36 KSI. Now, of course, what's going to happen, let me draw the rollers here. So there's the little cart, basically. What's going to happen if we zoom in on this part, I shouldn't have done that because it's a wheel. If we zoom in on this part, theoretically the contact is aligned. So in reality, what has to happen is the wheel has to flatten out a bit, and maybe even the material that the lower plate's made out of has to dip a little bit. And if you wonder if steel actually deflects, it's pretty easy to find out. The next time you're sitting watching a railroad or at a railroad crossing and the train's going by, look for a joint between the rails, and what you'll notice is at that joint, you'll notice it deflecting every time that a car goes over, or a car wheel goes over. It's really interesting to watch. So you begin to realize that there's more energy loss than just friction of air going past the train. There's also this motion of the rails that the engine has to overcome. But that's a topic for another course. Anyway, so the point though is that yes, the steel will deflect and it will flatten out a little bit. How do you deal with a problem like this? Well, the first key, we're asked about what's going on in the steel plate, but we really don't have anything to model it. The thing to note though is that this contact patch, if we were to expand it out, it's going to essentially be a rectangular shape. And really you're dealing with Hertzian contact stresses here, and that's not something we're going to delve into in a lot of detail in this book. There are, however, a couple of different things that we can use, and there's a recommendation that will make our life a lot easier concerning this type of problem in the section of your chapter that talks about bearing stresses. So if you have your book, and you should, open it up to page 151. And you'll notice in section 313, design bearing stresses, there's an equation, page 151, equation 323, that is talking about, let's see, I'll read it quickly. When rollers or rockers are used to support a beam or other load-carrying member to allow for expansion of the member, the bearing stress is dependent on the diameter of the roller or rocker D and its length L. The stress is inherently very high because the load is carried on only a small rectangular area. Theoretically, the contact between the flat surface and the roller is simply a line, but because of the elasticity of the materials, the actual area is rectangular. Instead of specifying an allowable bearing stress, the AISC standard, see reference 2, calls for the computation of the allowable bearing load RA from this equation. So here's the equation they give. RA equals SY less 13 times 0.03 times D times L. Now, there's no guarantee, of course, that these rollers are made out of the same material. However, one thing to note is that the elastic moduli of steels, regardless of their alloy, are about the same. So what that means is, of course, the contact patch has to be the same on the wheel as it is on the ground. And so, anyway, the point is that if we figure out what's going on elastically with the wheel, which is what this equation does, then we also know what's going on elastically with the floor with the ground. Now, while your author gave you a thickness of 1 1/4 inches, I think that was to throw you off. I don't think you need that unless I've missed something. So If you know that I've missed something, then please leave some comments in the area below on this video. But if you start saying things like, well, there's support on this piece of flooring, and so it's going to bend, and you need to talk about bending stress, we're not to that point in the course yet. So further, we don't know a dimension on this floor piece. So we can't really do anything with that. The only part we can deal with is the deflection in this local area, and that deflection is not going to be much. So there's plenty of material here to take care of that. So anyway, if we figure out what's going on and calculate an allowable load based on the wheel, that should be the same for the floor if the wheel were made out of the same material as the floor. It isn't, or it may not be. However, they will deflect the same, and so this should give us a reasonable estimate of the maximum load on the floor. So anyway, the yield strength, by the way, this is an English units equation, and so this term has to be KSI. These terms have to be inches, and that's what we've got, so it makes our problem easy. There is also a metric equation on the next page in case you ever need it. So 36 KSI less 13. I'll go ahead and put the units out here because they cancel nice. Basically, we're using 3% of this product. The diameter is the diameter of the wheel, and that was given as 3 inches in the figure. The length of the wheel was given as 8 inches in the figure. Notice the inches will cancel with the square inches, and we'll get thousands of pounds of load capacity. So this comes out to 16.56 kips, or thousands of pounds. Now, if the load is evenly distributed, so it's placed in the center of that base and not just above one of the wheels, well, then the load capacity would double because we have 2 wheels. So what I did is I assumed that that's the case. So for the case of 2 wheels, P is 2 RA, and so that comes out to about 33,000 pounds. This is quite a piano dolly, basically. It could move quite a heavy load without too much trouble. So that's the end of that problem.